8.3 specific heat. The specific heat is the amount of heat per unit mass required to raise the temperature by 1 degree Celsius. Every substance requires a unique amount of energy per unit mass to change the temperature of that substance by 1 degree Celsius. The specific heat, C, of a substance is a measure of this amount. C is equal to Q over M multiplied with delta T. Delta T is the change in the temperature where T final is deducted by T initial. SI unit for specific heat is joule per kilogram per degree Celsius. The historical unit is in calorie per gram per degree Celsius. Let's take a look at this table that shows the specific heats of some materials at atmospheric pressure. Looking at the water, as you can see at the right column here, it is given 1 calorie per 1 gram per degree Celsius. The historical definition of the calorie is the amount of energy necessary to raise the temperature of 1 gram of a specific substance, in this case the water, by 1 degree. It is equal to 4.186 joule or 1 calorie required in order to increase the temperature of 1 gram of water by 1 degree Celsius. From the definition of specific heat, we can express the energy Q needed to raise the temperature of a system of mass m by delta T as Q is equal to mc multiplied with delta T, where delta T is always the final temperature minus the initial temperature. When the temperature increases, delta T and delta Q are positive and energy flows into the system. When the temperature decreases, or negative delta T, Q will also be negative and energy flows out of the system. A copper block of mass 200 gram is heated by steam. It is then dropped into a beaker containing 500 gram of water at initial temperature of 30 degrees Celsius. What is the final temperature of the water in the container? Given specific heat of copper and water are 387 joule per kilogram per degree Celsius and 4186 joule per kilogram per degree Celsius respectively. Firstly, we take a look at the copper block. Given the mass is 200 gram and then it is heated by steam. So steam will have this temperature of 100 degrees Celsius. The copper block at this temperature, 100 degrees Celsius, is dropped into a beaker containing 500 gram of water at initial temperature of 30 degrees Celsius. So the question asks, what is the final temperature of the water in the container? Definitely, when they are in thermal contact, the copper and the water, what happens is actually, because of the temperature difference, they will have heat transferred from the copper block to the water. Then in this case, the temperature of the copper block will reduce and then the temperature of the water will increase. So we can write down the heat gained by the water. The heat gained by the water is going to be equal to the heat lost by the copper. For this parameter, which is going to be the heat, we have the equation mc theta, or the change in the temperature. Same goes to for the copper. To distinguish these two parameters, mass, we're going to label it as mass with subscript W. Same goes to the specific heat of water, MWCW, and then the change in the temperature, the final temperature minus with initial temperature, which is going to be 30. Right, so we're going to apply the same formula to the copper, MCU, CCU, and the change in the temperature is going to be 100 minus T, because they will eventually reach this same temperature T. Moving on, we're going to substitute now the mass of water, which is going to be 500 gram or 0.5 kilogram, because the specific heat is in joule per kilogram per degree Celsius. Specific heat for water is going to be 4186. T minus 30 equal to 200 gram or 0.2 kilogram. Specific heat of copper 387, and then 100 minus T. The final temperature of water and copper will be 32.49 degrees Celsius. 8.4 Work in thermodynamics processes. Energy can be transferred to a system by heat and by work done on the system. In most cases of interest treated here, the system is a volume of gas, which is important in understanding engines. All such system of gas will be assumed to be in thermodynamic equilibrium, so that every part of the gas is at the same temperature and pressure. Firstly, let's learn about the internal energy of the system. Internal energy with the symbol of capital E with subscript INT is the energy associated with the atoms and molecule of the system. It includes kinetic and potential energy associated with the random translational, rotational, and vibrational motion of the particles that make up the system. It also includes any potential energy bonding the particles together. Secondly, we have heat. Heat is the transfer of energy between a system and its environment because of a temperature difference between them. The symbol capital Q is used to represent the amount of energy transferred by heat between a system and its environment. Now, we are ready to learn work in thermodynamic processes. Let us consider a gas contained by a cylinder fitted with a movable piston and an equilibrium. The gas occupies a volume V and exerts a uniform pressure P on the cylinder wall and the piston. The gas is compressed slowly enough so the system remains essentially in thermodynamic equilibriums at all time. As the piston is pushed downward by an external force through a displacement, the work done on the system is W is equal to negative F delta Y, the force multiplied with the displacement. In this case, we're going to change F now will be equal to PA, and then this is possible because the pressure is the same everywhere in the system by assuming that the system is always in equilibrium. So work now is going to be equal to negative PA delta Y. Note that if the piston is pushed downward, delta Y is going to be negative. So we need this negative sign to make the work positive. And then the change in volume of the gas is equal to delta V. So where delta V is equal to A multiplied with delta Y. The cross-sectional area multiplied with the height. So in the end, the work will be equal to negative P delta V. So this is going to be the work done on a gas at constant pressure. As mentioned earlier, when we push the piston downward or by compressing the volume of the gas, the work done here is going to be a positive work. Work done on the gas is positive. However, the work done by the gas will be a negative work. Moving on, if we pull the piston upward, we are expanding the volume of the gas. The work done on the gas will be negative and the work done by the gas will be positive. The work done in order to compress a gas slowly can be represented by this PV diagram. The graph here is of pressure against the volume. When we compress the gas slowly, the initial volume will reach the final volume, and then at the same time, the pressure increases. In order to calculate the work done on the gas for this process, it is going to be equal to negative area under the graph. Or mathematically, we can write it down as negative integral P dV. We start with from the initial volume until the final volume.